the first thing is just basically safety and sort of sanitation tips. When you're working with malware, obviously, it's dangerous. It's liable not only to damage the machine you're running it on, but to infect it and place it under control of a hostile server, and for it to be used to attack other machines, like infecting them on your network. So you have different viewpoints about how careful you should be about sanitation. I went to the Honig Alliance training from Europe on how to analyze malware. They came to America a few years ago, which they don't do very often, and it was very interesting. It's one of the things that made me convinced I needed to teach this class. They had some simple sample malware to play, and they showed us some of these tools. But they discovered that in Europe, their standards are very high. They make a fake internet. The malware is in a virtual machine. It never can connect to the real internet at all. They make a fake internet that will reply to requests. And they found out that in America, people like from Norton and McAfee just run malware in a machine and let it phone home, let it be part of a botnet. But then you're participating in a crime and you'll appear on a list of infected machines. And there, yes, so what? Watch one more bot for a while. It's just the fastest, easiest way to do it, and we're trying to get the job done here. There's 1 million infected machines. Yeah, we're recorded as having a machine infected for a while. And that showed the difference, between the attitude. They were very precise and clean over there, and over here, they're just doing whatever gets the job done faster. Anyway, so whatever you do, you need to have some kind of safe environment where you have some reasonable assurance that you're not going to be infecting other machines on your network that you didn't intend to infect. So the logical thing most people use is virtual machines. You could use real machines that are air-gapped, and that would be the safest thing. There was a time, perhaps 5 or 6 years ago, when people believed that you could not infect air-gapped machines, but that's before the United States military targeted Iran, where they had air-gapped machines running their nuclear isotope separators, and they said, they're air-gapped, how are we going to take them over? And they said, well, even if it's air-gapped, you've got to bring in software somehow, so we'll infect the USB sticks. And so an air-gap is not perfect. There's also a very famous security researcher up in Toronto, I think, runs CanSec West. And he claimed that he bought brand new machines and they had been infected with malware that was sending supersonic sounds to other machines spreading across air gaps. And everybody said, you gotta be kidding, that's insane, that can't be true. And he posted some statements claiming they were true, proof of this and other people. I don't think he ever really convinced people. That is certainly possible, but it's very hard to believe that anybody is getting hit with something that exotic except targets of military. Like if you're the espionage guys, like the NSA and the Russians and the Chinese military and the Iranian spies and the Israeli spies certainly have these exotic capabilities, but I do not think they waste it on low-value targets like ordinary researchers and commercial businesses. Anyway, so you could infect a real machine and have no internet connection, and that might be fine, but then you really won't get to see what the malware does. When it tries to phone home, it won't be able to phone home, so you won't be able to pick up that traffic. It may well never even bother to do much at all, because if it turns on and can't reach the server, it may just shut down. So that's not so good. All right, well, by the way, one advantage of this is there's some malware that detects it's in a virtual machine. Normal virtual machines are not very subtle at all. There are many obvious clues that you're in a virtual machine. The adapter is named VMware Virtual Interface. It has a MAC address that comes from VMware Incorporated. There are registry keys. They were not designed to hide the fact that you're in a virtual machine, so there are a bunch of simple, easy tests that malware can use. But anyway, the most common way, just because it's cheapest, is virtual machines. That's what we'll do. Most of the time, it's fine. There are a few attacks that actually try to escape from the virtual machine into the host, and when those are discovered, the virtual machine software people patch them as quickly as possible because that is a serious flaw. One of the biggest ones I heard was about a year ago, Kimu, one of the enterprise class virtual machine things you run on Linux, had a really serious flaw that affected most of the cloud services like Amazon E2C, and because these virtual machines had virtual floppy disks by default, which nobody had thought about in years, and the floppy disk had some egregious flaw like a buffer overflow, and so you could just write too much data to the virtual floppy and escape from the virtual machine, and it was a big deal because it means everybody had to restart all their virtual servers to get the patch. But anyway, occasionally that happens, but it's not too common. Here, we mostly use VMware Player because it's free and runs on Windows. You get a lot of good features, certainly enough to do the work. The one feature you don't get is snapshots and rollback, which is what the pros use. The pros pay $150 for VMware Workstation, because then you can define a snapshot right before you install the malware install the malware, run it, see what it does, and then revert back to your snapshot quickly. For us, it would take about 10 minutes. You'd have to throw away the virtual machine and re-extract a clean one from your 7-zip file because VMware doesn't have an efficient snapshot, and that's what you get by using free stuff instead of the fancy stuff. But it amounts to the same thing, and all these other virtual machine things would be fine too if you can use them. The general principle is the same. Most of this malware was written for 32-bit Windows XP because XP code can run in almost any later version of Windows. It's usually the target. We're using Server 2008 because, of course, XP has its end of life. And then most of this stuff seems to run fine in 32-bit Server 2008, so that's a modern machine to work with. By the way, I saw one student unzip their Server 2008, get it running in VMware, and immediately run the updates. Don't do that. These things are old and unpatched for a reason. It is a good habit, of course. You should always run updates on a production machine, but these are deliberately vulnerable machines, and it's very likely that the updates will break the features we're trying to exploit. And anyway, all right, so in VMware, you can disconnect the network adapter and have a machine that is completely isolated. You can also have host-only network, which is what Microsoft uses in all their classes, because then they don't have to have antivirus on the machines. You have your little network with a member server and a domain controller and maybe a Windows 10 client, and they're networking to each other, but not to the internet. And if you want to put some software on them, you can download it in the host and then drag and drop it on the virtual desktop, and that way the host's antivirus gets to examine it, but you don't have to burden all your virtual machines with antivirus, which really messes them up and slows them down. But normally you want your malware to connect to the internet so it can just phone home. If you're going to take the sloppy procedure, which is the one I recommend, the American procedure, just letting it be really infected for a while, because we're just trying to do this the easiest, fastest way to find the answer, and we're willing to accept a small amount of collateral damage to do that. So if you put it in Ncat mode, that is usually your best bet, because that puts your virtual machine behind a virtual router, so you're not on the same layer 2 subnet as other people. I was practicing attacks one time in a coffee house, and I didn't realize I was in bridged mode, and I affected all the other customers in the coffee house. It was a very subtle effect that they wouldn't notice, which is lucky on my part. But anyway, that's unprofessional. That's why Ncat mode is there. Then everybody's on the other side of a virtual router, and that limits how much harm you can do to them. Bridged connects you directly to the local network, so you are a peer of every machine in the local subnet. So if you were working in the lab, you could have other physical machines in the lab see your virtual machine. And you might want that on occasion, but generally you don't, because that means they're all subject to attacks from your infected machine. All right. Like I say, you can easily, if you have a professional version of a virtual machine client, you can take a snapshot, launch malware, and then just revert back to the snapshot easily to get back to a known clean state. You can even make a series of snapshots as different stages of malicious activity go by, and that's good when you're analyzing complicated multi-stage malware. Anyway, so VMware, the risks are the malware may not run correctly in a virtual machine because it might just check for that. VMware may have bugs, and the malware may attack the VMware, and it may spread in principle to the host. So your host machine shouldn't have confidential data on it or anything when you're doing this kind of nasty work. Of course, all the textbook samples are harmless. They're imitation malware written for students to work with that has most of the properties of real malware, but it doesn't really spread or do much harm. One thing about the textbook samples is some of them do pop up irritating boxes and are a little bit hard to remove, so they'll kind of mess up a machine, but they're not anything really bad like real malware would do. So grab an iClicker if you don't have one, and let's do a few of these. All right. Did we use these last time? Yeah, okay, good, so people know how they work. All right. So just turn it on with the bottom button and answer these questions. Let me make this as big as I can. All right. So what's the network type you cannot do with a virtual machine? Quit at 35, I guess. All right, you can't really have an air gap. The virtual machine is sharing hardware with other devices like the host, and is not separated from them the way a real air gap would be. So it's never as safe as a real air-gapped machine. There was a big issue this. I heard of people in the Department of Defense that would have 7 computers on their desk because they were required to have an air gap between unclassified, classified, sensitive, secret, top secret, and people talked about cleaning up their desk and giving them 7 virtual machines on a host instead. And this is something worth considering carefully because that's really not the same. You might decide that it's worth a small amount of additional risk to do that, but it's really not the same as a real air gap. Anyway, all right. So which is the most hazardous? I'll quit at 30. All right, and that's bridged. Bridged puts you right on the same network as other machines and is most likely to expose them to your malware. All right, which one lets VMs see each other but not the internet? Therefore, not the type that we'll typically use, because the machines can't phone home and you can't observe that traffic. All right, and that's NAT. Oh, no, it's not. It's a host only. Host only lets you see machines on the same host, but not the internet at all. Quite limited in value for that reason. All right, what type lets the VM see one another and the internet, but has a virtual router protecting the other people in your room? All right, looks like I quit at 25. All right, and that's NAT, which is typically the sweet spot. This usually gets everything we want. Reasonable protection of other machines and reasonably accurate behavior of the malware so we can analyze it. All right, so since we talked about just the basic safety rules, now we can talk about how you do dynamic analysis. And it is amazingly easy, but it involves making a lot of assumptions that are not always true. And this is, like I mentioned before, this is a sloppy process. So the tools you're using fail, and sometimes they're wrong, and the criminals attack the tools, so you can't really trust anything 100%. So you've got to understand you're using sloppy procedures, and if you have trouble with one, just switch to another, and so you just need to have a good arsenal of tools to try. So the dynamic analysis is easy. Now, your static analysis, we tried before, basic static analysis is extremely limited. If you're not willing to spend a lot of time and reverse the assembly code and figure out what it's doing, your static analysis is pretty much looking at strings and submitting the thing to an antivirus engine to see if you're lucky and somebody else already did your work for you. But you're not going to get a lot farther with that. So the next step is dynamic analysis, which will get you a lot deeper into the malware without yet having to make a huge investment of effort to read the assembly code. So static analysis can also be stopped by obfuscation and packing, where you can't even see the strings. It's packed by something. In the homework, you have something packed with UPX, and if people are friendly enough to use that, you can get a copy of UPX and unpack it, but it's not very hard to write your own packer, just a simple little machine code routine, and then you won't be able to easily unpack it. So you'll be stuck with this packed junk you can't even see the strings in. And dynamic analysis is a trivial answer. Just run it, it will unpack itself and run and do its thing, and you don't really have to understand how it was packed or obfuscated. So the quick and dirty approach is sandboxes, and these things are ever increasing in popularity. For money, people will sell you or let you use in the cloud sandboxes that do all of this automatically. This is what FireEye does, and there's another FireEye product, Last Line, highlight thing. They take the email attachments that come through your email and they harvest them and they send them up to the cloud and run them in virtual machines and decide if they're malicious and send you a report. This thing is bad for this reason and that reason. And the report just does what we're going to do by hand. It runs it and it looks for registry keys that change and files that are created and network traffic. And if it decides it's malicious, it just lists all that and says, here you go. Here it is phoning home. Here's the files it creates as indicators of compromise. Here's all the registry keys to delete to clean it off. And you have a imperfect but quick and automated result there. So you can buy these sandboxes here or subscribe to services that do this, and that's cool. We're going to do it by hand here, partly because we don't have any money and partly because we're trying to learn how things really work. It's generally the case these days that there are a lot of powerful tools that will do security tasks, but I've had people come take courses, even though they're experts in those tools, because you really have to understand what they're doing to interpret their output and see what it means. And none of these automated sandbox tools are really all that smart. So it doesn't take too much effort for the bad guy to mess up the sandbox. And a manual analyst has the opportunity to add human intelligence into it. So, by the way, I met a student in one of these classes last week that heard about artificial intelligence, which is really coming, and thought we were all going to be out of a job because of AIs. And I don't think it's coming like that. I think we might have an AI driving Uber, and there'll be an AI in your $100,000 firewall trying to adapt to the virus signatures, but it doesn't mean you're not going to need human defenders, not anytime soon, in my opinion. Anyway, so you can't run DLLs in your malware. If the only thing you have in the malware is a DLL file, then that has to be loaded as a library to run in an exe, and there is a run DLL.exe included in Windows. Just to connect to a DLL, that's one way to do it. Then you can launch a DLL to analyze it. If somehow you have a DLL, but you don't have the attached exe. All right. You can refer to it here and have a command line that will run DLL and then run the DLL here. And there are various values and ways to refer to the imports you want to go in. Your DLL may have many ways to come in, which they typically do because it offers a whole series of library functions. And so when you run it, you have to tell it which one of those you wish to run. And that's what that number 5 is. Or this one here, you can refer to it by name, like an installer that will just have install and uninstall. And if it's a more complicated DLL with many entrants, then you might just refer to them by number to go to the one you want. Malware, there is one special import in a DLL, and that whenever it's an export of a DLL, that is run every time it loads to initialize it, and that is usually where malware puts their malicious activity anyway. But if they actually hit it in one of the other functions, then you might want to run them one by one. Process Monitor is a fantastically powerful tool, but it's like Wireshark. It makes way too much data too fast. And what Process Monitor actually does is watch the Windows Event Viewer. The Windows event logs are very thorough, but they're very opaque and hard to understand. And all Process Monitor does is collect all the event logs for a series of interesting events and present it in a nice graphical interface. But it makes so much data that it will fill the RAM and crash the machine if you just leave it on very long. So you wait until you're just ready to run the malware, you start Process Monitor, you run the malware, then after it's done its thing, you turn it off, and now you try to filter the results, which will now be 200,000 events you've caught. So you spend quite a while cleaning it up. Here's what happens just from launching Calc.exe, 253,000 events. So that's kind of stupid, but it's showing you all the events, everything that happened here. This is a registry opening a key. This is closing a file somewhere. Here's opening key. Here's reading the file, Calc.exe. Here's creating some files called DLLs, querying basic information. So even the simplest little program like Calc involves all these little actions happening, and you're going to record them all. So in order to get actual benefit from this, the first thing you have to do is to conceal everything that is not malicious, so you can focus in on the malicious things. So here's the structure of this thing. You've got start and stop with a magnifying glass. You can erase the events here, and you can filter the events here, which is going to be our best friend. And now we're here, you've got some default filters to look for just certain things like registry and file system only, which I haven't used much because that's certainly not something you want to do on the first pass. But in the projects you'll be doing this, you'll see if you learn how to use this tool, it's really very good. So one simple technique is to exclude normal processes, and one sloppy technique is to just exclude processes by process name. Now that is obviously risky. If a malicious process uses a process name of a genuine Windows process, we won't see it, but it is one option. Filtering with include seemed to be the way to do it. So I filtered this one by just with process name is calc, then include, don't include anything else, and that lowered it down to, as you can see, a reasonable number of processes. of things to look at. And I'll show you in the projects a little bit later how it looks. So that's ProcMon, Process Monitor. The next thing is Process Explorer. Process Explorer is the souped up version of Task Manager written by Mark Russinovich. Mark Russinovich is a fantastic guy. He was just like a student in college, and he got into Windows NT, and he dug deeply into Windows NT and figured out everything about how it worked, and he started contacting Microsoft with bugs in Windows NT, like a dozen bugs. And they were right, so they fixed them, he sent them another dozen. So they fixed them, they sent him another dozen. They could never get him to shut up. And they finally just bought his company and brought them in, because he invented all these tools that were so great inside Windows, and now they're building it all into Windows. And now he works at Microsoft, and he's running Microsoft Azure, and he really is extremely knowledgeable about Windows. He's the guy that found the Sony rootkit, because he installed the music, and it put a rootkit on his machine, and he immediately saw that. Wait, that was a rootkit. To him, it is as obvious as a bug landing on the monitor. And he has a standing invitation that he will clean malware off anybody's Windows system anytime. Because for him, it's easy. And not that easy for me, but he knows exactly what it should be running and can spot the one thing that's out of place and just pluck it right out of there. So he made these tools, and he made this one, Process Explorer, along with a lot of others. And this is what Task Manager should be. So let me bring this thing up live in my Windows machine here. It's good, clean fun. And in fact, Microsoft keeps adding more and more Process Explorer to Task Manager in each version of Windows. So here I've got, all right, Task Manager is here. And this is the old-fashioned Task Manager. These are applications I've launched, of which there aren't any. These are Windows processes, of which there are 58. And on they go. There's like CSRSS, and then there's another CSRSS. And if I sort by name and go down to something like task ends, there's 2 of them. And there's SVC host, there's about a dozen of them, all running with different process IDs. And I have no clue here why there are so many or what they're doing. So this is pretty lame and annoying, and very limited information. You'll have a lot more fun running Process Explorer. So here it is, Process Explorer. All Mark Russinovich's tools are so old school, you don't install them. They're often just a command line tool you put in C Windows System 32, and if it's not a command line tool, it's one exe file. He never bothers with all that complicated stuff, because he takes it simple. So here's processexplorer.exe, and that's how it looks. It has various panes, but if you just look in the top pane, it is what Task Manager should have been. Windows system processes run as pink. I forget what the blue stands for, but now here's SVC host, and it's showing me, if I hover over it, it tells me this SVC host is running a remote procedure call, which I mentioned before is a very important part of Windows and a very vulnerable part of Windows. A lot of viruses come in through here because it is a Microsoft technology that makes it possible for you to take a software component that was originally part of one program and expose it to the internet. And that makes it very easy to take your products and turn them into something you can sell, but it also means that a bunch of things designed for a closed, safe system are now exposed to threats on the internet without the security being improved. So it has led to a lot of security disasters, but also it makes it easy to sell software and make money. This one here is running the DHCP client and TCP IP, and this one is running group policy, and on it goes. Now I can see what they're doing in quite a lot of detail, and you can also learn a lot. So let's launch an app like Notepad. Okay, here's glorious Notepad. Okay, and now that I've launched that, there will be, down here is my desktop. Explorer.exe is the main process which starts and draws the desktop and the start button. It starts when you log in. So all the things that you launch are children of Explorer.exe. Here's these things running in the background like iTunes Helper and some VMware stuff and some stinking Java update stuff. And these are all these programs that felt like they should burden your machine forever with extra processes in case you're going to use them. And here's Notepad. So I can see Notepad down here. I can see the memory it's using, and I can see a lot more information about Notepad down here. Here are all the DLLs Notepad uses. Advanced Windows Library to show visuals, the kernel library. Here's other things down here, like a theme, and here's a spooler driver to print things. All these things are loaded by Notepad. And you can learn even more about it by adjusting more things here, and we'll be playing with that. But that's Process Explorer, and we'll be using it a lot. You can see exactly what's running. Okay, processes are blue, services are pink, and things turn green and red briefly as they pass through different states. Then you can see the DLLs that are loaded, like you saw there. You do that with view, lower pane view. It can be DLLs or handles. Handles are just named variables in a program. So a program might load 10 DLLs and it might have 1,000 handles. The handles are a pointer to a file, a pointer to a registry key, a pointer to a process, and typically you don't want to dig that deep unless you are the developer writing this code. But it is an option here to see all the handles. Now if you go to the properties, you see some real important stuff. Let me bring up properties here of Notepad. Properties here. Microsoft has a lot of security features. Like I said, they used to be the clown of security, deliberately ignoring security, and since 2002 they have changed, and now they have a lot of powerful defenses. And you can see them here. That's the environment variables. Here's the strings, by the way, of the process pulled from RAM. Remember I said if you had a packed or obfuscated executable and you run strings on it, you won't see them? But if you run it and go here, you will see them because this is from RAM, and it has to unpack to put it in RAM. So that's one way to see them. Here's security, various permissions of it, and let's see what else we got. Here's the image. Okay, this shows me the path to the image, the command line that launched it, the directory it's in, and it's going to show me more security information. Let me get back to my slides. The verify button, and this should show, oh there, down at the bottom, DEP and ASLR. Okay, this one has address space randomization enabled. These are two defenses which are extremely powerful. They came out in Vista, and they had the result. See, one of the things the CanSec West conference has is the Pwn-to-Own contest. People go there, and they have a series of brand new computers. And if you can take them over, they give you the computer as an award, which is a trivial amount of money, but people get famous through this. And every year, people take over machines. The Mac always goes first, because Macs are actually very easy to take over with targeted attacks. There's just not much in the way of spreading malware infecting them. But when they switched from Windows XP to Vista, for a whole day and a half, none of the hackers in the world could get in. Because Microsoft put in these two defenses, address space layout randomization and data execution prevention. And those two essentially killed the entire category of exploits called buffer overflows, because they mean that you do not even have any idea where you are in RAM. It's random. So even if you can inject code, you can't find it to run it. And the place where you put in data is marked non-executable in its permissions, so even if you can find it, it won't run. And there are ways around that, but it took the white hat community about 2 years to learn how to hack through that stuff. It was a big raising of the bar. In the 127 exploit development class, we'll talk about exploits and then exploits that can get through that. But and you can see whether one of the problems with these defenses in Windows operating systems is not every process uses them. If you run old software, it'll have these things turned off. And even parts of the operating system have some of these defenses turned off. So that is the weak spot. That's one simple way to overcome them, is to find something that doesn't have these defenses and target that. And you can see this has ASLR, but it doesn't have DEP. So Notepad might be considered a weak target in that regard. Anyway, that's one way to see it. By the way, there's a verify button here that will check the Windows disk file's file signature. I was just going through a Windows file, and I might as well mention this. This is probably good for this class. I was developing a project for 127 because I saw a very interesting blog post. And let's take a look at an example here of PuTTY. PuTTY is a harmless Windows utility that lets you connect to SSH. So here's PuTTY, and if you want to know what's going on with PuTTY, one thing you can do is run LordPE on it. LordPE is a great tool. LordPE is intended to analyze portable executable files. When you first load it, it shows you the processes running in memory, and you could analyze one of them in RAM if you wanted to. And we will do that later on in this class to analyze running malware that's obfuscated. But you can also analyze portable executables as disk files. So I can edit the PE, and I can load PuTTY, and it will show me the PE header. Now this is kind of esoteric, it's just where various parts of it are, but to get something easy to see, you hit sections. And this shows you the portable executable sections that we talked about last time. You have the text section where the instructions are, you have 2 kinds of data, and then a resource section. Those 4 sections are all there are in PuTTY. So that's good, clean fun. Now, so here's what I was doing for a hacking project. When you want to put a Trojan horse in poison an exe file, you have to find some place to put the new code. Now, the sloppiest way to do this, but the simplest, is to add a new section. So you add a section header, and then you edit it, and you give it some size. Its virtual size is going to be 1,000, and its raw size is going to be 1,000. So now I have 4,096 bytes, that 1,000 is in hexadecimal, an extra section in my code where I can put malware. Then all I have to do is alter the code to jump in there and execute it. So what I thought I would have to do at this point, when I was following a tutorial written years ago for an earlier version of PuTTY, and they said, after you do this, it won't run anymore. It claims to have 5 sections, but there's nothing there. So when you run your modified version of PuTTY, you'll be sorry. And if I go up here and run my PuTTY, it runs. So I said, why is that? So I tried this, which was pretty telling. If you open this, I'll just open it in HXD, that's all you have to do. Because I tried adding text at the end of it with a hex editor to hit the new section, and it didn't work. And here's why. PuTTY is now signed, and it did not used to be signed. But you can see the signature. All you have to do is go to the end of the file, and if you go through those 4 sections, you escape from them, and at the end of the file is a couple of thousand bytes of this stuff, which is not junk. Chiark, greenend.cord, some kind of PuTTY path. This is what a digital signature looks like. And you're going to see stuff like thought.com. This is the certificate path of a signature that signed this file. And that means, so I thought I'd mention this because it's important. If you look at PuTTY, you can check the signature. And now the signature is so broken, it doesn't even show up. If I get the original PuTTY file, let me name this. This is PuTTY 5. It now has 5 sections. Let me get the original from my host so I can show you this is an important thing to do. .exe. Oh, it's in my downloads folder. I don't know why this thing is failing to find it. There. PuTTY. There. All right. Okay, now I got a clean copy on the desktop, and that'll do. Let's go to my desktop. Wait, it didn't copy? That's VMware tools. VMware tools are very, very unreliable things. Try it again. Yeah. All right. So somewhere on this desktop is PuTTY. There. And if you go to the properties of a signed file, you will see a digital signatures tab that tells you who signed it. And you can go to details, and it will show you the signature, and it will tell you this signature is okay. That means not one byte of that file has been altered. It cryptographically, the checksum matches the checksum in there. And if you modify anything about that file, which I'll do now, let's open HXD, and open that file on the desktop, which is, in fact, I'm going to not destroy my original, just a moment. Let's take the original PuTTY and make a copy. Good. There's PuTTY copy. That's what we're going to alter. HXD. All right. Open the PuTTY copy. If I can find it. There we go. Okay, and the first byte is 4D. I'm going to make it 5D and save it. So I've changed 1 bit in that file. And now that I have, the copy no longer shows the right icon. That is Microsoft's attempt to make this obvious. And if you go to Properties and Digital Signatures, it will, whoa, tells you it's okay. That's not right. It shouldn't be okay. But anyway, it should have detected that, and I don't know why it has failed here, but that's the cry for the course. Anyway, I just wanted to show you how it works, and that's the point. You can check the signatures for signed files. I don't know why Microsoft operating systems don't always check the signature and refuse to run if the signature is bad. iOS and Android apps do that. But Windows apps just run cheerfully with an invalid signature or no signature, so I can just put malware on top of the signature and it will just keep running, which is pretty rude. But anyway, that's the game. You can see strings in memory, and you can compare them to strings on the disk, and they'll be different if the program is packed or obfuscated. So if you open a document and you wanted to see if it's malicious, something like a Word document or a PDF, you can just open it with the vulnerable application and watch in Process Explorer to see if it launches extra processes. Malware usually does. And you'll see it in the image tab of that property sheet. You can take registry snapshots. This is what Regshot does. Regshot is a tool, you load it, and you take first shot and second shot. You'll see those two buttons over there. So you load this thing, you download the malware onto your system, you're ready to go, you take a snapshot. Then you install the malware, then you take a second shot, and then you compare them. And it will show you all the registry keys that were changed by running that malware. Very simple task, and you get this long notepad file full of registry changes, but it's an easy way to do it. By the way, Process Monitor will give you the same information as a whole bunch of registry write operations. It's just a different way to view the same information, and it's easier under some conditions to use one tool or the other. There are many tools that overlap, and that's good because each tool has a high failure rate. All right, and then there's faking a network. If you don't want to let your malware phone home, which is often a good idea, then you can simulate it. Now there's a product recommended in the book called a PATI DNS that will hijack DNS. I was never able to make this tool work on any system. This is the second time I've had a popular tool that everybody swears by that just won't run on any of my systems. There's a Linux tool for man-in-the-middle attacks that everybody uses and it just doesn't work. Anyway, there are other tools that work. So I don't know what's the problem with this tool, nor do I care. There's a perfectly good tool called INetSim in Kali, which we're going to use instead, which simulates the internet. And that one works. So whoever designed that tool might care why it doesn't work, but I don't really care. I just want something that will work. Now, if you want to simulate a server, the simplest thing you could do is just have a listener. And all this will do is the handshake, sin, ac, which is not necessarily enough to get the behavior you want, but it is the simplest thing to do. You can use Netcat, or in Windows, you can use Ncat, which is part of Nmap. I highly recommend installing Nmap, even just to get Ncat on Windows. And then you can listen, and you can at least tell that it did attempt to connect to this server on that port. But if it then continues to send data and you want to see that data, you might not get it with this simple listener. So here's what you'll do. I could just, on a Windows machine, I could just run ncat-l80, and that will start listening on port 80. And since that port is below 1024, it's a privileged port, and you must have administrator rights to listen on it. And now, if I connect, my web browser will not say, I can't find the server. It will connect, and then it won't be able to find the web page because it's able to do the handshake, which means the server is there, but when it sends an HTTP GET, it doesn't get any answer because this is not really an HTTP server. It's just simulating the first stage. So that's why this is probably not really good enough to fool your malware. It's good enough to detect a little bit about the network traffic, but to do it right, you really need to serve something because, you know, of course, really loading a web page requires sending up GETs and getting responses with HTTP headers and all that jazz. So this is what a proper load of a web page looks like. You get something with HTTP, you find the host and so on, then you get a response like this, all full of data, and some of it's encoded or zipped. That's what you should see. So INetSim is much better, and that's what we're going to use. INetSim is a very simple program. You just run it in your Linux, and when you do, it will then simulate about a dozen servers. Every common service, FTP, Telnet, HTTP, HTTPS, it will just simulate them all, and what you do is you change your DNS server to point to INetSim because it will just answer the same IP address for every query. So the whole internet is on that one box, so it doesn't matter what domain you go for, which is important. Otherwise, it'll go connect to a real server. And then you can open anything you want, any URL in the browser, and it'll be this page because it's always going to the same server. But that's a pretty good simulator. That way, your malware will connect to something that will really handle reasonable exchanges. And if you run Nmap on INetSim, it will tell you that it's running all kinds of stuff. Telnet, DNS, HTTP, HTTPS, SMTP, POP, you know, all the common services are there, which is what you want. So whatever your malware is trying to find, it will probably find it, and you can analyze it. All right, so in practice, I say here's the general rules. Procmon, you filter on the malware executable name. So you see only things running under that process, that technique, and clear all the other events prior to running it. That's one fast and dirty way to focus on the interesting events. Process Explorer, you can just run and see. And Regshot, you know how to run that. You take one snapshot before and after running the malware. You can use a virtual network with INET SIM if you do not wish to let your malware phone home. And then you can just use Wireshark to see what traffic it sends. All of this is kind of insane. You're running these tools on the compromised operating system, which is going to get infected. So that's why you have to realize they might get fooled and lie to you. But if the malware author did not think of that, then you'll get accurate information from these tools. I was surprised when I saw this. It seemed to me like at the very least I would run Wireshark on the Linux system, running INET SIM, so I'm not running any tools on the compromised operating system, but in practice, this works. And you just do, for your first pass, you just do whatever you can to make it easier, even at the cost of losing some accuracy. So here's an example of the virtual network. Your Windows virtual machine is here. The DNS has been set to go to a fake DNS server, like they're using a PATI DNS, but I use INET SIM. And everything goes over to the Linux machine for all the internet traffic. So it's actually fetching everything from my Kali machine. So I got a few eye clickers about that stuff. And I'll just say a few words about the projects. All right, what kind of file can run directly? I'll quit at 25. All right, only the EXEs. The DLLs cannot be launched directly. All right. What tool can listen on any port? I'll quit at 25. All right, and that's Ncat, the command line tool. The rest of them are limited, but Ncat can listen on any port and send to any port. Wireshark does not listen on any ports. Wireshark just shows you the traffic that's passing through an interface. It's not a listening. There's no way you connect to Wireshark. It's just like a magnifying glass, watching what's going by. All right, and which tool pretends to be the whole internet? All right, I'm quitting at 25. All right, so that is INET SIM, of course. Good, a popular answer. All right, let me just see who got the most right, and then I just want to talk a bit about the projects and make sure everybody's ready to go. Don't need that. I do need that iClicker thing. Here, iClicker thing. All right. Open gradebook. There we go. Export. We're getting there. Okay. And all right. So the 8s have it, which is 28, 52, and 85. Now let me just say a few words about the project. Make sure everybody is aware. So stuff is going to start being due next week on 2.6, projects 1 and 2. They are all down here. So project 1 and 2 are basic static techniques, and you could run them in a virtual machine, or you could even run them on a Windows host if you're willing to be sort of sloppy with your normal Windows host. Here you just, you get the lab files, which will cause your antivirus to go nuts. So I highly recommend using a virtual machine with no antivirus. Then you send some stuff up to VirusTotal to analyze it. You analyze it with PEView to look at the header and see basic information about the file, and then PEID to recognize what kind of file it is and what language was used to create it. And then you look at the strings with any of a variety of strings tools. And last one is run Dependency Walker to show the DLLs it uses and the imports and exports, just by looking at the header. So those are basic techniques. And here you do a lot of these techniques again. This time the file is packed. So when you run PEID, it will tell you it doesn't know what it is, but it was labeled UPX, which is your clue that it uses the common UPX unpacker, which you have to run. This UPX unpacker is a 32-bit code that for some reason won't run on a 64-bit system. So again, I recommend a virtual machine, and then you can unpack it and find the strings. So if you don't have a virtual machine, you should get them here. There's a Windows 2008 virtual machine you can use, and I think it goes through some of the information how to do it here in the iNet Sim project. This is where you set up this thing. You have to set up 2 virtual machines, a Kali machine, and a Windows machine. Unless you have some other kind of Linux you like, you can use any kind of Linux, it doesn't really matter, but you have to figure out how to get iNet Sim running on it. iNet Sim is built into Kali, so it's easier. Anyway, you download a 7-zip file from Kali, unzip it, and you have a Linux machine. You download the Windows 7-zip file from me, and you've got your target machine. So here's your target machine running Windows 2008. Here's your Kali Linux machine running. You have to make sure that they're on the same network so you can ping from one to the other, which is the #1 mistake most students get stuck on. They put one in NAT and the other in bridged, and they can't see each other, and of course nothing will work. So when you have problems, the first step is always ping from one machine to another. I should mention, every time you have networking problems, do this. First, ping from one machine to another. Then, turn off all firewalls. Then, run Wireshark at both ends to do whatever you're doing. This will usually get you to the end faster than anything else. See what is being sent and what is really being received. If you do things in that order, you can usually get to the bottom of almost any networking problem. Anyway, so here's your Kali machine, and you can check to make sure it's not already running a web server. If it's a clean Kali machine you just downloaded, it won't be. If you've been doing a lot of projects, you might very well be running a tool that runs a web server, because a lot of hacking tools run web servers because the author is too lazy to write a GUI. So they just write a web page, and you control it through a web page. So this is the command lsof-i that shows you if something is already using port 80. And so, for example, I was running Apache, and I have to stop Apache before I run iNet Sim because only one tool can be listening on a port. So there's an iNet Sim configuration file. And you do need to adjust a couple of things here. There's a service bind address, which you can set to your IP address. So all these listening services like DNS and FTP and HTTP will be listening on that address. You can also just set it to 0000. This way it'll just listen on every address, on every interface, and that's fine for our purposes. It's simpler. But the one thing you really have to fix is this DNS default IP. Every time it makes a DNS query, it's going to tell it to go to this number, and you have to make this point to your Kali machine. Otherwise, nothing will work. So that's the main thing you have to do. Then you install your Windows machine, put on Nmap, so you've got Ncat, and now you have to set your DNS server to point to the Kali machine. So every time you try to go to a domain name on the Windows machine, it will get a lie from Kali, and the lie will point to Kali, and it will try to fetch every website from that machine. That's what you want. And then you can just open a page, put yourname.com, anything you want, any domain, doesn't have to exist, because whatever it is, the malicious DNS server will lie and say it's here, and you'll see this page. So that's what you can turn in to show that you got it working. And then you can scan it with Nmap, and you'll see that not only is it doing web pages, it's serving up every other common service, which is the default situation. And that's the joy of iNet Sim. And after that, now that you have a fake internet, you can then do dynamic techniques using your fake internet. So this is the 3rd chapter stuff. You use your Windows 2008 machine, you run this software, download the tools you're going to need. You need to have the lab files, PEView, strings, process monitor, all these tools you needed on your machine. You probably already have them, but all the downloads you have to do first, because when you change the DNS server to point to the fake internet, you can't download anything anymore. So once you've got them all, then you can examine the malware in PE view, look at the strings, and get ready for dynamic analysis. So this is the step I was just talking about today. So first you start INET SIM, so it's got a fake internet to phone home to. You set the DNS server to point to INET SIM, so now your Windows machine is sandboxed. It will not go to the real internet anymore, it'll just go to your fake internet. Then you run Process Explorer, so it's available to see what's happening. You run Wireshark, so it starts sniffing. Then you start Process Monitor as your last step. Then you exclude harmless processes by taking everything that's already there and excluding it by name. You'll have to exclude 10 names on a Windows machine you're using, so that the Process Monitor just sits there empty. It's picking up thousands of events, like 91,000 events, but they're all being filtered out. But anything that doesn't match those filters will be new processes launched later, and now you run the malware. And when you run the malware, Process Explorer will show the malware running, labo301.exe, and Process Monitor will show about 10 events. And then you can stop it and analyze those events. And so you get down to just these 2 events. These are the ones that are critical to us. It writes a file called vmx32to64.exe, which is a name to try to look like part of VMware, to make people think it matters. And it sets a value in the run key to make it automatically run at startup, which is a very common persistence technique. Every piece of malware will if you run a process, it will typically not survive a reboot. So to make it survive a reboot, you have to make some kind of permanent change in the system that will automatically launch it. And these things are called auto start extensibility points. And it's one of the more crazy parts of Windows that there are about 50 ways to automatically launch software on Windows. So it is actually very difficult to enumerate all the software that's automatically launching. And the malware authors have found the most hidden, esoteric ones of these to use, of course, to make it launch in a way that you will not be able to stop it from launching. And so that's the game here. You'll see the event that showed that it set this registry value, and the registry value is a run key in the video driver. So your operating system thinks that this is some process that has to run in order to show video, and therefore starts it automatically, and it's really malware. And then INET SIM is keeping logs of everything it does. So you'll see when you stop it all, there is a log here, and in the log, it will show you what happened. And in particular, in this case, it will show you another indicator of compromise, that there was a DNS request for practicalanalysis.com, and that's the command and control server. So your logs in your INET SIM show you what domain it thinks it went to, and then what traffic it sent to that domain. So you see the DNS name of the command and control server here, and if you look at the actual packets it sent, by looking for that, you can find the query that found it, and then you can find the phone home message here. And for this particular part of malware, it sends 256 bytes of random traffic to the command and control server. And this is something you look for. You've now found the persistence mechanism, so you know how to make it stop relaunching. You've found the indicator of compromise on the disk in the form of a file it created, and you've found the network indicator of compromise, so you can now scan network traffic for a whole company and find all the infected machines by looking for that traffic. And those are the big goals we look for here. You want to know what the malware did, how to find it, and how to detect how many infected machines there are. That's in this simple example, you're going through the steps. And this is one of the steps of incident response, which is the larger container. The malware analysis is part of incident response. You have a bad thing happening, and your analyst creates the indicators of compromise, which are then used to hunt through the company and find all the infected machines. So that's the big picture. I think I'm going to stop the recording, and if anybody wants to work on this stuff in the lab, I can help you there. Let me just quit this. This is 126, chapter 2, I think.